Hello everyone, my name is Diaz from the University of Burgos in Spain, and I'm going to present the work with the title Modeling Hydrogenation during cold well fatigue of additively manufactured titanium alloys. This is a brief overview of the contents. Cold well fatigue and hydrogen embrittlement in titanium alloys will be introduced. Then the numerical framework will be presented. After that, the influence of selective laser melting on the choice of parameters will be discussed, and followed by a brief presentation of the main results. The choice of titanium-64 is based on its very good mechanical properties, similar or even better than, for example, high-strength steels, but with a lower density, so this is perfect for lightweight applications. The use of additive manufacturing has been very common during this last decade, due to the need of complex or customized geometries. However, as we know in our field of structural integrity, these methods strongly influence microstructure, and so the mechanical behavior. Despite the very good properties of titanium-64, creep processes happen even at room temperature. Some failures involving cyclic loading and also sustained loads, as we can see in this loading scheme, have been found, and this is called cold well fatigue. Here we can see a failure attributed to cold well fatigue of the fan hub that caused the failure of the whole engine of an Airbus aircraft in 2017 and requiring an emergency landing. Other common process is the failure of titanium alloys due to hydrogen, and this is usually known as hydrogen embrittlement. Some manufacturing processes, such as welding or electroplating, introduce hydrogen, and this can be outgassed in a baking post-processing, but of course this increases the production cost. Hydrogen uptake can also happen in service, especially in electrochemical reactions or when titanium is in contact with gaseous hydrogen. As we can see in these two failures, hydrogen embrittlement is also critical in biological environments. Here we see a fracture of a titanium-64 mandible implant attributed to hydrogen embrittlement. And similarly, we see how cracks are nucleating in a hip implant due to hydrogen absorption. This accelerated cracking when hydrogen is present in titanium alloys is attributed to the formation of hydrides, which is a very brittle phase. In titanium-64, which is an alpha-beta alloy, as you probably know, hydrogen transport and hydride formation is more complex. Alpha phase and alpha prime, which is the martensite that is usually formed during SLM, are hexagonal closed-packed phases and have lower diffusivity and lower terminal solid solubility than the beta phase, which is a phase-centered cubic crystal. And so the presence of martensite will in principle delay hydrogen diffusion, but increase hydride formation. We must also take into account that embrittlement is strongly influenced by hydrogen kinetics, especially during cyclic loading, such as the case of 12 fatigue. Here we can see a nice scheme of how the formation of hydrides takes place and promotes cracking in an alpha-beta alloy. When hydrogen enters, beta phases has a much higher solubility and diffusivity, so hydrogen atoms tend to accumulate in beta grains. However, due to the different strain dilatation and solid solubility, stresses are developed in the interface, leading to the formation of geometrically necessary dislocations and also hydrides. After that, due to the high amount of hydrides and dislocations, cracks nucleate and propagate. As we have already mentioned, SLM produces the formation of martensite, as we can see in this figure. This alpha prime usually takes a lamellar shape, but the shape and the size strongly depends on printing parameters, for example on hatch spacing or on scanning velocity. This transformation during rapid cooling does not only influence hydrogen diffusion and hydride formation. Martensite is also a harder phase, so higher stresses are going to develop. This is the equation governing diffusion, and here we can distinguish between hydrogen in lattice sites and trapped hydrogen, or hydrogen in trapping sites. The magnitude F represents the hydrate volume fraction, and 1 minus F is added to include the rate of interstitial hydrogen which is forming hydrides. Trapping term can be regarded as a sink term, and it depends on the number of trapping sites, but also on the binding energy of those traps. An important term here is included within the flux to reproduce hydrogen accumulation in tensile regions, which is very important for fracture. This term is proportional to the hydrostatic stress gradient. Here we are assuming a scalar value for the lattice diffusivity, but to consider anisotropy we could implement, for example, a diffusivity tensor. But here, for simplicity, we are just analyzing two limiting cases. The case where hydrogen diffuses parallel to the faces, which is a much faster situation than the case where hydrogen diffuses perpendicular to the faces. Now I'm going to briefly mention two key points for hydrate formation modeling. The terminal solid solubility is the concentration at which hydrate formation starts, and this value depends on hydrostatic stress. We must notice that this term, for the common parameters, is always negative, so the higher the hydrostatic stress, the lower the terminal solid solubility. Other important aspect is that a rule of mixtures is considered for the equilibrium solubility. The rate of hydrate formation is determined by a simple level rule until the concentration reaches the limited value for hydrogen atoms. All this framework follows the work of Lufrano, so more details can be found in this reference. The implementation of both hydrogen transport and hydrate formation is performed in a user subroutine in Abaqus, and we exploit the analogy with heat transfer equation, so we use a U matrix T, and the concentration in lattice sites is solved using the temperature degree of freedom. However, for the hydrate volume fraction, we cannot use this degree of freedom, and we just implement a forward Euler scheme. It is important also to note that we will not discuss dilatation and hydrogen modified plasticity, but these are critical phenomena for environment, and we have also implemented the corresponding equation using a user expansion and a user hardening in Abaqus. So in future research, we are going to also discuss all of these processes. To study hydrogen accumulation and hydrate formation, we consider the typical bundle layer approach, in which a crack with a small radius is loaded with remote displacements. These displacements are proportional to a stress intensity factor, and they follow the theory of linear elastic fracture mechanics. We use a user displacement subroutine in Abaqus to make this loading automatic, and we reproduce a cyclic dual distribution for the stress intensity factor. We must recall that the context of this study is to predict possible effects of selective laser melting on hydrogen transport and hydrate formation. So we have to consider possible modifications in microstructure and so in the parameters. For example, the building orientation can produce anisotropy. As previously mentioned, we only analyzed two limiting cases. Another input parameter that will surely be increased by the selective laser melting is the fraction of martensite. We can recall that the alpha prime, the martensite, has a lower diffusivity and also a lower solubility than the beta phase. And we also can predict that distortion in the microstructure due to the rapid cooling will also promote a higher number of traps. Finally, residual stresses are not modeled, but of course would influence the process. After these considerations, we define four hypothetical materials. Number one assumes parallel diffusion and a low martensite fraction. Material number two assumes the same low martensite content, but a slower diffusion because of the perpendicular phase arrangement. Number three can be compared with number one because the only difference is the higher martensite fraction. And finally, the material number four has the same parameters than number three, but with 100 times the density of trapping sites. Here we must say that for number 1, 2, and 3, the number of traps has been related with an intermediate dislocation density for titanium-64. Here we do not consider different yield stresses for the sake of simplicity, but of course, the higher the martensite content, we should consider a hardening effect in the yield stress. Considering this presented numerical framework, we simulate hydrogen redistribution during dual fatigue. We can see here, on the right, the maximum hydrogen concentration in lattice sites normalized by the equilibrium concentration. This is plotted with the black lines, and we can see how the maximum increases because hydrogen diffuses to the fracture process zone. Comparing a martensite fraction of 0.1 with 0.5, we can see that at the beginning, a higher martensite fraction, the dotted line, results in a lower concentration because diffusivity is lower in comparison to a material with a higher content of beta phase. However, when hydrate starts to form, the formation is faster for a high martensite fraction, as expected, and so the hydrogen concentration increases faster. If we plot this normalized concentration and also the hydrate fraction in the crack plane, this is the distance from the crack tip, we can see this peak of hydrogen accumulation. First of all, we can see that for the lower diffusivity limit, this line, this represents perpendicular diffusion. Hydrogen's transport is so slow that the peak does not appear. For parallel diffusion, the materials 1 and 3, 2 peaks appear. This one and this secondary peak. The first one is formed due to the hydrogen entry from the surface and also to the stress-modified diffusion. This means that hydrogen tends to accumulate in tensile regions. However, a second peak is produced by the decrease in terminal solid solubility. We have already discussed. So we have a competition between hydrogen accumulation and hydrate formation near the crack tip. Here we analyze the effect of a hypothetical trapping multiplication by factor of 100. This could be produced, for example, by an excessive distortion during rapid cooling in SLM. And here we plot hydrogen distributions after only 5 cycles. We can see that the higher amount of traps, the lower available lattice hydrogen, and so the lower hydrate volume fraction. However, for longer times this effect is weak, and all of these trapping processes also depend on the binding energy of traps. To sum up, we recall that the objective of this work is to predict how selective laser melting is expected to modify microstructure, especially the martensite fraction, and this will affect their response to hydrogen environment. This modeling framework is complex, especially for an alpha-beta titanium alloy, but here we have demonstrated that hydrogen accumulation and hydrate formation can be implemented. For time reasons, we did not discuss strain dilatation or modified plasticity, but we have already implemented this phenomenon in Abaqus subroutines. The following step is to predict crack propagation using the couple of our framework with phase field models. And of course, we are also starting with experimental testing on titanium-64 produced by selective laser melting to verify our model predictions. And that's all. Thanks for your attention. If you have any doubt or comment, you can contact me in the following email.